In this video, we're going to talk about comparison tests for integrals. So first of all, comparison tests for integrals, why would we use these tests? Why wouldn't we just integrate, right? So when we can't determine if an improper integral converges or diverges, then a lot of times we just use a test just to know at least that much information, because sometimes you can't evaluate the integral. So there's two tests that we're going to talk about. The first one is the direct comparison test. So for this one, we say if f of x and g of x are continuous on the interval from a to infinity, and this is important, you have to have this relationship of 0 is less than or equal to f of x is less than or equal to g of x. So as far as what you choose for your f of x and your g of x, it will, this will kind of determine the next part of the problem. So check this out. So this relationship has to hold for all x greater than a. So if g of x converges, then f of x also converges. But now look at the other part of this. If f of x diverges, then g of x also diverges. So when we go back to this, so if g of x converges, f of x converges. So I think that, like, if you think about the nature of this inequality, that does actually make sense, right? If this converges, this is like overlapping this. So it makes sense on some level that they should both converge, versus if this diverges, then this diverges. I always think of it as like this function is like swallowing up the other one in its divergence. So it matters which one is going to be your f of x and your g of x. So you can choose your other integral, but it just has to strictly follow that criteria. So let's start with this first one. So I've got the integral from 1 to infinity of e to the negative x squared. So this one you can't integrate as is. You can try, but it's not going to happen. You can't use substitution. It's going to be hard to like really use any other techniques to really get this done. So instead, what we're going to notice is I don't know anything about e to the negative x squared, but I do know something about 1 over e to the x, right? And more specifically, I know that this one will be greater than this one because this is going to end up having higher powers of x, so that's going to make this overall number larger. So therefore, when the denominator is larger, if this denominator is larger than this one, then overall this number will be smaller. So you just got to keep that straight, right? Okay. So anyways, so I have this relationship here. So the question is, what do I know about 1 to infinity of e to the negative x dx? So this we can definitely integrate. So I can go ahead and I can integrate this. So this is an improper integral. So I will go ahead and I will integrate, and I just have to switch this to an a and then evaluate as a goes to infinity. So here is my antiderivative, and I can plug in my limits of integration. And so ultimately, I don't actually really care necessarily what the answer is. All I really care about is that an answer exists at this point. So since an answer exists, that means that this limit converges. And so if this converges, then again, because we were using, remember, this whole thing here, so in the relationship of this, so my larger function converge, therefore the smaller function will also converge. So what that means is this function here, or this integral here, will also converge, and so at least I know that much. Okay, so now let's look at a different one. So I've got from 1 to infinity of 1 over the square root of x squared minus 0.01. Okay, so something that can be a little intimidating sometimes is like, how do you decide what to compare this to? Because this looks like a really weird function. So I have some tips on simplifying how you think about that. So if there's like some number in here, that's usually inconsequential in the big scheme of things. So usually what you're interested in is what is the largest term, usually in the numerator or denominator. So that's kind of what's known as our dominating term. So I noticed that this x squared is kind of dominating the bottom, but then I have to take the square root of that. And so if I take 1 over the square root of x squared, that really equals 1 over x. And so then I just have to decide, okay, what is the relationship between 1 over x and 1 over the square root of x squared minus 0.01? And in this case, 1 over x is going to be less than this, because ultimately I am subtracting a little bit away from this. And so since I am subtracting a little bit more away from this, this will end up having a slightly smaller denominator than this. So that's why that relationship will hold. Okay. So now we need to think about what's up with this integral. And this is like a classic integral that over time you won't even need to do the work for this. Like this is one of the integrals where you just kind of know what happens, but let's talk about it. So for this particular integral, so I'm going to take the limit as a approaches infinity now up from 1 to a of 1 over x. So here's the deal. When I integrate this, I get the natural log of x. And so when I plug in my limits of integration, the natural log of a as a goes to infinity, this whole thing goes to infinity. So what ends up happening, this equals infinity. So since it doesn't equal a number, right, infinity is not a number, what that means then is that for this situation here, this integral diverges. Therefore, because of the relationship of this, since this was the smaller integral, that means that this one will also diverge. So that's kind of the way that you can think about this, and you will eventually notice just some like classic integrals as you learn more about improper integrals, and you'll get better at making your comparisons. Now, there is another comparison test. The other one is called a limit comparison test. So for this one, so this says let f of x and g of x be positive continuous functions on some interval from a to infinity. So if you take the limit of f of x over g of x and you set that equal to L, so L has to be some value less than infinity but greater than 0. So if this limit exists, then what that means is either both of these integrals converge or both of these intervals diverge. So if this has an answer, then you don't have to worry about like which one's larger, which one's smaller. It's just if this division has an answer and you know something about one of these two integrals, then either both converge or both diverge. Okay, so let's take a look at a couple of examples of this. So I typically like to still set up like close-ish functions to what my original function is. And I've talked about this particular function in other videos, so we actually already know what's going to happen with this one, but let's pretend for a second that we didn't. So just how could I use the limit comparison test here? So first of all, I've got that x squared as once again the dominating term. So I am just going to compare this function here with 1 over x squared. And so what I'll say is that we know that 1 over x squared, this converges. So as long as the exponent here is greater than 1, these always converge. So now we know this converges, so what can we, hopefully this also converges. So now we can go ahead and run this test. So the way that the test is going to be run is, so I take that 1 over x squared over 1 over x squared plus 1. So now, of course, I can simplify this to get x squared plus 1 over x squared, and then I can just do some division here. So I've got the limit as x approaches infinity of 1 plus 1 over x squared. And this, so this right here is going to go to 0, so this value of this limit is 1. So since this has an answer, remember, either both converge or both diverge, and since we know that this one converges, we know that that limit will also converge. Okay, so now let's try a slightly different one. So now what if I just change this so that I'm taking the square root of x squared plus 1 in the denominator? So once again, I am just going to compare. So since I've got this as my dominating term, so I've got the square root of x squared, I'm going to compare with 1 over x. And as we know, right, 1 over x diverges. So let's run this test. So sometimes when you are working with some of these limits, sometimes funky things can happen. So this is one where a funky thing's going to happen. So I set up, okay, so I set everything up, I simplify everything, right? And so what I notice is I'm getting infinity over infinity, so I can use L'Hopital's rule and take the derivative of the top and bottom. So if I take L'Hopital's rule, here's the derivative of everything. And so now what I'm going to do is, now that I have everything kind of set up, I can see these 2's will cancel out. This part here can move to the denominator. I'm left with x in the top. So what you'll notice now in like working with some of these limits is you'll have to kind of make some decisions on this. This looks very similar to what we started with, right? And so once again, I've got infinity over infinity. So I can use L'Hopital's rule again, but you can see now if I try to simplify this again, or if I set this up, now I'm back to where I started. So just a reminder, some people may have forgotten this, L'Hopital's rule can sometimes fail and just cycle, and this is one of those cases where it cycles. So you do also have to think about when you're working with some of these limits, sometimes you have to just think of all that limit knowledge that you have. So going back to the starting point, this is where I was. The other thing that I could do, so this is a limit as x approaches infinity. So the classic like first trick that you learn in a Calc 1 class for dealing with things as x goes to infinity is you just divide by the highest power in the denominator. So in this case, I want to divide everything by x, but keep in mind, so I can't divide this square root by x because you can only divide something into a square root if it has a square root. But what I do notice is that if I write x as the square root of x squared, these two things are equivalent, and now I can divide this top part by this, that's all good, while I can divide the bottom by x, and I'm literally dividing still by the same thing, right? I'm not upsetting the value of anything. So anyways, so now I divide everything. So now I've got everything's being divided by the square root of x squared here, everything's being divided by x here. So I'm left with now this situation here, and so now when I take the limit, I get the square root of 1, so this just equals 1. So again, what does this test say? This test says if there is an answer, then either both diverge or both converge. And so since we are comparing with 1 over x, since we know that this one diverges, that means that this one also diverges. So that's the idea behind that. Okay, so I'm going to leave it at that. If you want to hit the like button or the subscribe button or leave me a comment, that'd be super cool. And otherwise, I will talk to you guys in another video. Peace.